Hello everyone, I welcome you all to the subject Electromagnetic Field Theory. Here we are in chapter number 6, Capacitance. In the previous video, we have gone through the Poisson's and Laplace equation. We have seen the popularity of both these equations in engineering applications because in most of the applications we know what is the actual potential supply that is given as input to that particular application, so that the net capacitance effect we can predict with the help of Poisson's and Laplace equation. Now, the charge configuration and the potential are the two major parameters into consideration for calculation of exact capacitance of any device. Now, the charge configuration we have seen of several types: point form, line form, sheet form, or distribution of charge over volume, ring, disk, that way. Now, Poisson's equation we have simply seen del square V is equal to minus rho V upon epsilon, whereas for the Laplace equation the condition is that there is no volume charge distribution. So out of the various types of fields, the configurations, the different fields may have different potential values, the different space rate of change of potential, that we say potential gradients. So if we are interested in one of the potential field, so that time we have to see the solution of the Laplace equation, which has involved the all types of charge configuration except the volume charge distribution. So let us see the details of solution of Laplace equation. There are several ways or methods opted for finding the solution of Laplace equation. We opt a very simple approach. See, the Laplace equation is given by del square V is equal to 0. So finally we have to find the value of V which satisfy this particular equation. That time we will say that it is solution of Laplace equation. So we opt the reverse way. So initially V we consider to be the potential onto a plane. Let us say the plane formed by xy. Hence V is a function of small x and small y. Okay. So therefore the del square V we can write that is del 2V by del x square plus del 2V upon del y square is equal to 0. So we have taken second order partial differentiations of the electric scalar potential V with respect to x and y, when V is a function of x and y only. So now let us put this to be the equation number 1. The reverse way what we opt for this one is we assume that V value is something x into y in capitals, where x is the term formed by small x only and capital Y is the term formed by small y only. So that time V will be the solution of this Laplace equation. So it will have this form. So if we substitute V is equal to xy into this Laplace equation, we shall be obtaining it del square capital X capital Y upon del x square plus del square capital XY upon del y square will be equal to 0. So it is in general second order partial differentiation with respect to x for capital XY, which is the assumed solution of V. So x is term of small x only, y is term of small y only. Y does not involve any x, that is why y is a constant here. So in the second term, similarly, capital X is a constant. So the constant can be made outside of the differentiation. Hence we write the next step capital Y del square capital X upon del x square plus capital X del square capital Y del y square will be equal to 0. So I put this equation to be equation number 3, and whatever the solution we have assumed, V is equal to capital XY to be the equation number 2, whereas the Laplace equation for only two parameters in the plane xy, we have equation number 1. So equation number 1, 2 and 3. So we have this form. To make this term of only x and to make this term of only y, we divide it by capital XY. So dividing both sides of equation number 3 by capital XY, we obtain 1 upon capital X del 2x upon del x square plus 1 upon capital Y del 2y upon del y square is equal to 0. So by dividing capital XY to both these terms, we got this form. So this is 1 upon capital X del 2 capital X upon del x square. So this is the term of x only. This is the term of y only. If you substitute the value of x and y here, so it will be a constant. Okay. So now to the next step, we assume that the constant represented by these two ones will be like this. From the above equation, we can say 1 upon capital X del 2 capital X upon del x square will be equal to minus 1 by capital Y del 2 capital Y upon del y square. So I have just shifted the second term from the previous equation to the right hand side. So we suppose these two brackets are same here from the above condition. So we substitute these one to be the constant represented by alpha square. Okay, and we call this alpha square to be a separation constant. Okay, because from only one equation form here, after substitution of these one terms by alpha square, we can obtain two types of equations. So this alpha square will be equal to, the alpha square will be equal to 1 upon capital X del 2x by del x square will be equal to alpha square, and del 2y upon del y square will be equal to minus alpha square. Yes, this is 1 upon capital Y in multiplication way. So these equations further we can use this to be the equation number 4, suppose this to be the equation number 5, this to be the equation number 6. From equation number 5 we can write del 2 capital X upon del x square will be equal to alpha square capital X. Capital X from the left hand side into the denominator it was, we have shifted to the right hand side. So getting this form of equation, okay, we can find the standard solution. Okay, the standard solution in hyperbolic form will be capital X is equal to A, where capital A and capital B are the constants. So this is one form of solution to this form of equation. Another in exponential form can be given as capital X will be equal to A dash e to the power alpha x plus B dash e to the power minus alpha x. So these two are both the forms of solutions for the above equation. So let us denote it by equation number 7, this by equation number 8. Now we have similar equation in the form of y. So that equation, that is del 2 capital Y upon del y square will be equal to minus alpha square capital Y. For such type of equations, the standard solution is given capital Y will be equal to c cos alpha y plus capital D sin alpha y. So let us say this is equation number 9. So for the x part we have solutions by 7 or 8, and for the y part we have solution by 9. So using equation number 7 and 9, what we have assumed v is equal to capital XY, we can get v equal to, in first bracket we have a cos h of alpha x plus b sine h of alpha x in multiplication with the second bracket by the y. So this is x, the y will be c cos alpha y plus d sine alpha y. So here capital A, capital B, capital C and capital D, these are the constants. When we know the values of this A, B, C, D, our solution of capital V or the Laplace equation will be completed. Now here we involve the boundary condition, the boundary between the perfect conductor material and the dielectric material, what we have seen in one of our last chapter video. So here we apply the boundary condition. The boundary condition as such, first of all the solution I mentioned, capital V will be equal to capital A cos h of alpha x plus capital B sin h of alpha x in multiplication with C cos of alpha y plus D sin of alpha y. So for this equation, if we put the condition that V is equal to 0 and x is equal to 0 for all y, because we have considered capital V to be the potential into the xy plane. So if we get x is equal to 0 for all y, V will be equal to 0. Similarly, V is equal to 0 and y is equal to 0 for all x. So by considering these two type of condition, we get capital A is equal to 0 and capital C will be also equal to 0, because capital A involves these two terms. So finally, the form of capital V will be capital V1 sin h in bracket alpha x into sin alpha y. Here V1 is nothing but V1 is equal to capital B into D, because the two brackets are in multiplication. By putting A is equal to 0, the first term will be equal to 0. The first bracket will be left with B sin h alpha x only. The second bracket, after substituting C is equal to 0, will be left with D sin alpha y. So B into D, we are substituting capital V1. So it will be sin h alpha x and here it will be sin alpha y. So this will be the form of solution for capital V. So V1 we have substituted capital B into D. Now to look at this particular equation, that is capital V is equal to V1 sin h alpha x sin alpha y, we can say that the capital V will be equal to 0 if we make sin alpha y to be equal to 0 by substituting y equal to 0 or y is equal to pi upon alpha or y is equal to 2 pi upon alpha, because the sign value for these y will give you 0 in multiplication with all, capital V will be equal to 0. Or we can make sin h alpha x, this term, to be equal to 0 if we substituted x is equal to 0. It will be sin h of 0. So finally we can get 0 multiplied by these two will be equal to capital V equal to 0. Finally, we want the equipotential surface, and equipotential surface at capital V1 we can obtain by substituting capital V will be equal to V1. So V upon V1 will be equal to 1. We get the form capital V is equal to V1 sin alpha x sin alpha y. So substituting V equal to V1, we get sin h, this is h, sin h alpha x sin alpha y will be equal to 1. So we can represent this equation as alpha y is equal to sine inverse of, in bracket, 1 upon sine h alpha x. So this type of equation in graphical form we can represent like this. On the diagram, if we have the two axes, capital X axis and capital Y axis, these are the X and Y axis intersecting in this point. Hence here it is X is equal to 0, Y is equal to 0, where we have thought of the potential to be equal to 0. So at Y is equal to Y by alpha, okay, and at, yes, here we can draw a line where V will be equal to 0 entirely. V will be equal to 0 if we put Y equal to 0 for all X. Similarly, V equal to 0 where we put X is equal to 0 for all Y. And the condition alpha Y is equal to sine inverse 1 upon sine H alpha X, we obtain such type of curve. Here I can write alpha Y will be equal to sine inverse 1 upon sine H alpha X. So here the condition is V is equal to capital V1. So this way we have tried a simple approach to obtain the potential. So the simple relation should be, remember that C is equal to Q upon V. So here we were finding the solution for capital V first of all from the Laplace equation. So further we can follow those steps to get the charge configuration, and finally the capacitance effect for the electric device will be into the consideration. In the subsequent lecture, we are supposed to calculate some parameters based on to the solution of Laplace equation. For getting more information onto the subject electromagnetic field theory, you can subscribe to Ekeeda channel. Thank you.